on to a problem where we have a graph of the voltage across a capacitor given as a graph, and we want to determine and plot the corresponding current. So when you have a capacitor, we have the voltage, we want the current, then you go back to your formula sheet, or you remember that the current across a capacitor, I, equals C dV dt. And you remember that derivative just means slope. And so all we have to do to get the current is to find the slope on each of our segments. So we have from t less than -4, we have -4 is less than t is less than 2. We have -2 is less than t is less than 2. And we have 2 is less than t is less than 4. So our current is going to be the capacitance times the slope. Well, the slope is 0 less than 4 and t greater than 4. The slope is 0 for t less than 4 and t greater than 4 and between -2 and 2. So for those, that's just C times 0 equals 0 amps, and C times 0 equals 0 amps, and C times 0 equals 0 amps. So no work to be done there. Now, between -4 and -2, just remember slope is rise over run, and pay attention to your units. Here we're in volts and seconds. There's no millis or anything to worry about. So between -4 and -2, you go up 100 and over 2. So our slope is 50. Our capacitance is 20 micro, so that's 20 times 10 to the -6. So 20 times 10 to the -6 times 50 equals 0.001, I believe. It's 1,000 microamps. 100 milliamps. No, I'm looking in the wrong place. Yeah, 1 milliamp. I don't know why I put 100 on my graph. 0.001? 0.001 amp, which is the same as 1 milliamp. And then between 2 and 4, you go down 100 and over 2. So that'd be -50. So this is 20 times 10 to the -6 times -50, which is -0.001 amps, or -1 milliamp. So if we're going to graph that, we'll do a graph like this. So time in seconds. Current. It'd be nice to put it in milliamps because then it's 1 and not 0.01. So we have 2, 4, -2, -4. So, okay, so I have a bad habit on tests, especially with zeros and ones. It's like I'll multiply I'll multiply 0 times 1 and get 1. And most recently, I had a new one. I subtracted 0 minus 0 and got 1. So I don't know where I come up with these things. So apparently I started counting backwards. So that's a new one for me. So 2, 4, negative 2, negative 4. And we had 1 milliamp and negative 1 milliamp. And the 1 milliamp was between negative 2 and negative 4. And the negative 1 milliamp was between 2 and 4. We had 0 before then, and 0 between, and 0 afterwards. And in engineering, I've noticed they do like to connect with vertical lines. So we'll have those. So that's the graph. Now specify the time interval during which power transfers into the capacitor, and that are those during which it transfers out of the capacitor. So power in and power out. Well, power in means it's absorbing. That would be positive. Power out means it's supplying, and that would be negative. We know that power equals I times V. Notice that V is positive. It's never negative. So V is always greater than or equal to 0. And between negative 4 and negative 2, I is also greater than 0. So a positive times a positive is a positive, so the power in would be between negative 4 and negative 2. And power out would be negative, and that would be when the voltage is positive but the current is negative, and that would be between 2 and 4. So the next question is, at what instant in time is the power transfer into the capacitor a maximum, and at what instant is the power transfer out of the capacitor a maximum? Well, we can see that we have power in from negative 4 to negative 2. And if you look at what you would get if you multiplied these two graphs together, you can see you would have your highest point right here at negative 2. That would be the biggest number here times here. And so you have your max power in at t equals negative 2. And conversely, where are we going to have our smallest one? That's going to be, now remember we have to think smallest negative. That's going to be at this point right here at positive 2, because that's going to be where we have our maximum number in the negative direction. So max power out at t equals 2. What is the maximum amount of energy stored in the capacitor, and when does it occur? So energy is 1/2 CV squared, and we have it, the max energy during this entire time right here, because that's where we have the biggest voltage, is 100 volts. So this is going to be from -2 to +2, and it will be 1/2, and the capacitance is 20 times 10 to the -6, and the voltage was 100 volts, and you square that, and I have that this equals 0.1 joule, but I am not to be trusted. Yay! That makes me happy. Okay. Question 5. After plotting the voltage waveform, obtain expressions and generate plots for I of t, P of t, and W of t for a 0.2 millifarad capacitor. The voltage waveforms are given by, and so this was from a problem that had several parts, and I just picked this part. Okay, so when I graph one of these kinds of functions, I like to pay attention to where a change is happening, because the unit functions, the unit step function and the ramp functions, they're 0 everywhere, and then a change happens. So I want to see where a change happens. The change is going to happen for this one when t equals 0, and this one when t equals 0, this one when t equals 2, and this one when t equals 4. The 10, a unit step function, just is 0 until you get to 0, and then it goes up to 1, and then it's 1 from there on out. That's a unit step function. If you multiply it by 10, like this one right here, instead of going up to 1, it goes up to 10. So that's what this second one looks like. But 10u of -t means it's reflected across the y-axis. That means that it's going to be 10 on the left-hand side until it gets to 0, and then it goes down to 1. So 10u of -t looks like this. That's 10. That's 10u of -t. Okay, so putting these all together, the only one that has anything going on less than 0 is this 10u of -t. And less than 0, it's at 10. Now when it gets to 0, it drops off the face of the earth, it's gone, it's 0. But then we start with 10u of t, and 10u of t starts at 0 and is 10. So we just actually keep going. And then we have our next change at 2. And at 2, we have a ramp function. And you look at the number in front to see what the slope is. The slope is -5. So that means for every 1 you go over, you go down 5. So when I get to 3, I will have gone down 5. And when I get to 4, I will have gone down all the way to 0. And then I have another ramp function, and this is adding 5. And what that does is we had a slope of -5. This adds 5 to the slope, and now we're at a slope of 0. So that's our graph. So our function, if we wanted to write it out, this is a voltage waveform. V of t equals 10 for t less than 2, and it equals 0 for t greater than 4. And then in between 2 and 4, we know we have a slope of -5. So we know we have a slope of -5. And then let's just remember how to write an equation of a line. So our slope is -5. And I'm going to pick a point that's on this line. I'm going to pick the point 4, 0. And then I know, if you remember, y minus y1 equals m times x minus x1. Same thing here, it's v. So v minus 4 equals -5t, v minus 0 equals -5t minus 4, or v equals -5t plus 20. So minus 5t plus 20 for t between 2 and 4. Okay, so I of t equals c dv dt, and c is 0.2 milli, as it's 0.0002. So it's 0 for t less than 2, because the derivative of 10 is 0. The derivative of -5t plus 10 is -5, so I'll have -5 times 0.0002, which is -0.001, for t between 2 and 4. And then greater than 4, we're at 0 again. Okay, power is V times I. And that's going to be 0, and then -0.001 times -5t plus 20, and 0. And then the energy, which is 1/2 CV squared, is 1/2 times 0.0002 times the voltage at this time was 10 squared, which equals 0.01 joules. This is 0.5 times 0.0002 times the voltage here was -5 plus 20 squared, which is minus, or 0.0001 times I forgot a t, minus 5t, minus 5t plus 20 squared, and 0. And these were the intervals, the same time intervals as before. Okay, I'm gonna skip the next one, and if I have time, I'll do a video for it later. I want to make sure I get through some of the other stuff. And then if I finish everything else, more time, we can come back to it.